Okay, so the Atwood machine. Quick look at this. It looks like the B is a little bit bigger. I see a free body diagram that has some lines. And usually after you see the free body diagram, you're going to have something that has you derive an equation with Newton's second law. Not every time, just most times. It looks like that's the case over here. And then they always do something weird to it, like make the surface different, add more mass, take away mass. Who knows? So that's kind of the basis of things. And I'm going to look at this real quick before I get too far into it. And I see free body diagram and I see derive. So just for my own purposes over here, um, right on at the top of part B, I'm just going to write Newton's second law, like the equation for it. I'm going to pretend like this is all paper. Ah, sorry, there's like a motorcycle outside. In the figure above, two boxes, one with a mass of M large B and another with a mass of M small b, are attached to a thread that's mass may be considered negligible. Magic Disney string, it's there, but it has no mass for some reason. The pulleys are considered to be ideal. That means they spin without friction. They have no mass. They're there, but they're not there. Um, and the mass of large B is greater than the mass of small b. Okay, so the picture is kind of right. The boxes are initially held at rest and released. So yeah, this one's pretty straightforward. So might want to write this to start off with. Mass of large B is greater than mass of not so large B. And that means that the weight of large B, and the subscripts aren't so great with a pen, is going to be probably more than this one. This little one is probably going to be pretty small. And little b, g. And since they're tied together, we know that the system's probably accelerating this way. I mean, this part of the system is going up, and then this part would be going down, but like the magnitude of the system would be constant. Is constant. You don't have to write all that. I'm just writing it just to kind of show you. And if you look at these, you know that you have tension, and the tension in this string or whatever is all the same. Let me show you why. You have, if you had two spring scales, and I applied a force like this way to one, and then I had a friend apply force this way to two, we could never get those if they were held perfectly flat and there was nothing like, blocking one of them or anything weird happening, then we could never get them to read different things because of Newton's third law. Anyway, so yeah, the magnitude of force 1 would be the magnitude of force 2. Now, what if we tied a magic Disney string, massless, it's there but it's not there kind of string to them? Well, it would be the same thing. You couldn't get them to have different readings. And in this case, each spring scale would be measuring the force of tension, just the magnitude of force of tension, because it's going the opposite way. So it would look like this. Force of tension 1 is equal, the magnitude of force of tension 1 is equal to the magnitude of force of tension 2. Basically, the scales would have similar readings. If you hold a string between your hands, you can kind of maybe feel that. That's how an Atwood machine works. We assume that the magnitude of acceleration is the same, and the magnitude out through the system, and the magnitude, the force of tension is the same throughout the string. Okay, so back to the problem. So the boxes have been released. We did the acceleration. Yeah, and just based on what I just said, the force of tension will be going up on this one and up on this one as well. And the force of tension, you can't really see it, this is not the greatest free body diagram, it's just from my own notes, is going to be the same. I would say this, F. That's supposed to be an F. F sub T, force of tension and acceleration of the system are constant. Okay, so the two dots depicted below represent the forces acting on each box. Notice how they say each box right here. That is super important. that means you are not looking at the whole system. You are just like, you can cover up what little b, box little b, while you look at the large one, and vice versa. It says do not draw components. That is not a problem, being that there are no angles. Okay, all vectors, they mean the arrows representing the force, should be of a length relative to the magnitude of all forces. Basically, these lines matter. If a force is larger than another one, you need to make sure it takes up more lines than the smaller one. Okay, in case I haven't said it 5 million times before, do not use pen on free body diagrams. Get your pencil. You should have lots of them. If not, raise your hand. The proctor will bring you one. And way far away from the sacred diagram here, I'm going to just draw my acceleration as a reminder to myself of each box. We know that the whole system is going down because of the weight of box B. So I'm going to put acceleration. And that would be, if we just looked at it, this means B would be accelerating downwards. As it does that, it would bring the whole system, it would move the whole system with the same magnitude, and this would make box little b go up with the same magnitude of acceleration. All right, those are nowhere near these. Those are off to the side. You can scratch them out when you're done. Okay, so I know that box B has a weight that is pointing down. First thing you do, draw the arrow in pencil, and I'm going to label this weight large B. So that's mass large B times the gravitational field, also called acceleration due to gravity. And I know that it's got a force of tension pointing upwards that is less because it is accelerating downwards. So I'll label that F sub T. You can actually write the word tension, but I like abbreviations. Okay, so we're ignoring that one. It's over. The only thing we know about box B in relation to this is that they happen to have the same force of tension. So it needs to be, I drew this one 2, this one needs to be 2. Force of tension. Okay, and now this one's accelerating upwards, so that means that your weight needs to be less than your force of tension. Ooh, I didn't really give myself much room here. I have to draw really tiny. It needs to touch the dot. Weight of little box. I'm going to put mass, little b, g. And this is the free body diagram. Okay, and the points for this, you got 2 points. And if you drew the 2 weights and this one was smaller, then you get a point. If you drew the 2 forces of tension and it was smaller than the weight of the big box and larger than the weight of the small box, and it was equal, both forces of tension, then you got another point. Okay, so in part 3, this is the 3.1. It's the derived thing that usually comes after your free body diagram. And so I wrote net force equals mass times acceleration. This looks useful. Go ahead and circle that and put that down here. It says in the terms of mass of little b, mass of big B, and g, derive the magnitude of box B's acceleration. I went ahead and just brought this picture over here. Again, this isn't part of my answer. This is just what I drew in the original picture. What I'm going to do first is, I know that box B's acceleration is equal to that of the system's. Okay, or I should say the magnitude of acceleration. And what I'm going to do now is, that would be useful to add into my Newton's law equation. Okay, so I just subscripted my Newton's second law, which I have my arrow drawn down, so mass of the system and acceleration of the system. And I've indicated that these two are equal to each other. So now I need to put this, equation together with my free body diagram of the whole system. So that's kind of what I drew on the picture. You could redraw it, but I wouldn't. Okay, so mass of the system, acceleration of the system, they're going to equal, well, the thing that's making the system accelerate is the weight of the larger blocks. I'm going to write m sub b, so the mass of the larger block times the acceleration due to gravity. That'd be like your big force, but I'm going with what the drawing says here. And then the thing that's kind of slowing it up, or I mean, that's kind of going the opposite of the acceleration of the system, is going to be the weight of the little blocks. So I'm going to subtract them. I'm going to put m little b, the mass of little b, times the acceleration due to gravity, also called gravitational field. So this is Newton's second law. Something important to note, the mass of the system. It's not just for one block, it's for the entire block. And since the string doesn't count, it would be mass of the system would equal mass big B plus mass little b. So I would want to go ahead and solve for the acceleration of the system and plug this in. Okay, so what I just did was I solved it. I just divided by mass of the system to get acceleration of the system by itself. And then I said that acceleration of the larger box, because of the statement that I wrote over here, is equal to weight of the larger box minus weight of the smaller box. And then I just plugged in the mass of the system over here. So the way the points work on this are for having basically this, where you applied Newton's second law to the entire system. So mass times acceleration, and then the net force, big minus little or whatever, you get a point. Okay, for recognizing this, and for recognizing this, those two things together, you get a point. There are no half points. So you either had them both or you didn't. And for your final answer, which I should have boxed in, you get a point. So that is 3 points. Okay, so last section. They have to add something or do something weird. A new box A, which has a mass of m sub A, is added to the system as depicted in the figure below. Note, the coefficient of kinetic friction mu between box A and the table is 0. That tells you two really important things. It tells you that the table is frictionless, so no force of friction. It also tells you that this thing's probably still accelerating, so nothing weird happened to stop the table. To stop the system. Now we just have this block A added to the system, which basically increases the mass. That seems like something I just did. This. So we can do that. Here's how I would handle this. I would figure out a relationship between the magnitude of the acceleration right here and the mass of the system. And remember that mb plus, oh, I made a mistake up there. That should say little b. I don't know why I wrote mg. Be careful. So they do the weird subscripts. M big B plus m little b is the mass of the system. It should be like this. I might not lost the point for that, but I might have. Hard to say. But anyway, I'm going to take this equation and come up with the proportionality down here. Okay, so your answer should look something like this. Based on my work in part B, they'll know what that means, or just B, acceleration of the large box is inversely proportional to the mass of the system. See, over here. And then I put adding m sub A to the system increases the mass of the system. Therefore, the acceleration of B, the magnitude of acceleration of B, decreases. Here's what you would have gotten a point for. Points for. 1, recognizing that the mass of the system is inversely proportional to the acceleration of the box. 1 point. And for saying that the magnitude of acceleration decreases. You have to have both to get the points. So that is the Atwood machine.